Let's look at, for the AP class, because you're probably rolling in here now, let's look at question 16 for tonight's homework. I like to call this the Mets question after a former student because, if you solve this, the full way through, you can come up with a little equation that will always tell you the distance things act, okay? What we have in this problem, though, is this is a Torricelli, or a tortellini, as we call it. What we have here is our classic large, tank of water resting, in this case, on the ground, okay? It's filled with water, 10 meters high, so it has a depth of 10 meters, and like always, a tiny hole, a hole much smaller in cross-sectional area than the upper surface of the water, is opened up 5 meters upward on the side of the tank. We just want to learn how far away from the tank will the water land. You see here there's a hint. You don't need a calculator for this at all. We can think back to kinematics and how far an object moves each second of free fall. We'll think about that in a second, okay? So if we take a look at this, let's just draw ourselves a little picture. We'll go to the AP world here, add a new page. This is the intergalactic problem, number 16 for fluids. If we draw this container, it's resting on the ground. Even though it looks like it's hovering here, it's totally resting, I swear. It's 10 meters high, filled with lovely water, or if you're my late class in the day, milk. And we open up in the side of it a small hole. And this small hole is sitting at 5 meters off the ground, okay? Water naturally will with some velocity. Now, if you haven't seen Torricelli's equation or you're uncertain of what that is, check out an old video I have. It's called AP2 Chapter 10, Torricelli's Theorem. It looks through Bernoulli's equation, the big old Bernoulli, and it looks at the two assumptions we make to create Torricelli's theorem, that being that the pressure 1 is equal to pressure 2, so they subtract away from each other. And we also believe that the velocity of the water dropping is essentially zero. Okay, we know it's not truly zero, but for the sake of that container is so wide and has so much area to the top of it, in such a teeny weeny tiny little hole on the side, that water is going to shoot out and it's going to barely lower the container, and it's going to take a while. So we can say essentially that velocity is zero. Doing that, what we know from Torricelli is that the velocity at which this exits the container is going to be equal to the root of 2g delta h, where delta h here is equal to the depth you are beneath the surface of the water. So this is the delta h here, okay? And if this whole thing is 10 and we're 5 meters up, that means this has to be 5 meters, okay? G is our local gravity. That's our classic 9.8. And 2 is the number 2. We square root all of that. Ta-da! Now, the other thing we need to recognize in this problem is since this water is coming out horizontal, it's going to funk onto the ground. And since this water is coming out horizontal, it's really a x velocity. So if we start thinking about that, hey, this is coming out, we've got gravity, it's an x velocity, what we're thinking about is projectile motion. And for projectile motion, we know that this x velocity won't be slowed down because, as always, we're ignoring air friction and resistance here. And what we need to do is we need to try to figure out the amount of time this object is in the air. Because if we're ultimately trying in this problem, trying to figure out how far away has this object gone, if we read here, how far away from the tank will the water land, then what we need to do is, well, a velocity, especially in the x direction, multiplied by a time is going to give us some distance or displacement. So I have Vx, 2g delta h, and I know all those values. I know the delta h, I know g, I know 2. The question is, what's the time? How long does it take for this thing to fall down? Well, if we go back to good old projectile motion, we know that my favorite equation, which is that the displacement equals the initial velocity times time plus 1/2 AT squared, exists. We also know here that if we're talking about how long is this object in the air, how long does it take to fall down, we're looking at the y direction here. We're looking at up and down, okay? So while I wrote this out for the standard kinematic way, talking about the x direction, really this equation more closely resembles, if I wanted to write it out, a change in y displacement equals an initial y velocity. And because this is shot perfectly horizontal, our initial y velocity is 0 times time plus, so there's our 0, plus 1/2, well, the acceleration in the y direction is good old gravity, so that's g t squared. Our 0 doesn't really do anything here. And what we quickly find is that the time is equal to the square root of 2 delta y over g. Okay? So that's how long it takes for it to fall down. Yeah, plus minus, but it's only going to be the plus because time's got to be positive. Okay? So if we just go ahead and sub these quantities into a velocity times time, we will get, let's see, root 2g delta h times root 2 delta y over g. That equals our answer, our displacement, how far it goes. And maybe we remember this from math, maybe we don't, but if both of these quantities are in the square root, we can multiply them just like the square root isn't there, and then put the square root back in later. Okay, so if I look at these quantities and I multiply them, ignoring the square root, I know that 2 times 2 is 4. I know delta h times delta y is just delta h delta y. Okay, whatever. But I know g divided by g, those values are going to cancel. And then since I was just ignoring the square root, I can't forget about it. I got to throw it back in. That gives us how far the object is going to travel based off of how deep it is underneath the water and how high up it is above the ground. And for our problem here, if we kind of look at it, if we wanted to, we could say the square root of 4 is 2 and pull it out. I like to keep it on the inside. I don't really care. But square root of 4 times 5 meters for the depth of the water times 5 meters for the height. We've got 5 times 5 is 25. 25 times 4 is 100. Square root of 100 is 10. Woo! So that object goes 10 meters. Now that was working it out with all the math and plugging everything in. This equation becomes very helpful if you're ever given any random depth at any random height above the water. You can automatically just find how far it goes, square root 4 hy. But you could solve this problem, without having to work back to, the time equations for kinematics. You could think about just the fact that if this object is falling 5 meters, if you know gravity is approximately 10 meters per second squared acting downward or inward, then that means that this object is going from 0 to 10 meters per second in a second. That means its average velocity over that amount of time is 5 meters per second. So on average, if you go 5 meters per second and you need to travel 5 meters, it takes you exactly 1 second. Okay, so we're traveling for a second here. If we look at this time, we see like 2 times 5 is 10. 10 divided by about 10 is 1. Square root of 1 is 1. Yay, 1. We also see here for the Vx, we've got 2 times g times delta h. Well, in this case, delta h is 5. 2 times 5 is 10. 10 times g, which is about 10 seconds, is 100. 10 times 10 is 100. Square root of 100 is 10. So we know our velocity. Velocity of 10 times a time of 1. 10 times 1 is 10, which was our answer anyways. So in this particular instance, we didn't actually have to work out a lot of math. We could have just thought about this a little bit and really just done the Torricelli equation right here and just recognize that, yeah, it's going to take about a second to fall. Or we could work it out in completeness using this wonderful equation right here. With that, that's finished. Wow, I sneezed.